Hi, today I'll be reviewing AP Chemistry Unit 9, Applications of Thermodynamics and Electrochemistry. This is the last unit of the AP curriculum for AP Chemistry, so we're done. So let's get started with 9.1, an introduction to entropy. So entropy is basically the dispersal of matter in a sample, and changes of entropy can be described as a measurement of how dispersed the matter is in the system. So this diagram here shows how entropy increases, and entropy basically increases as matter becomes more dispersed. And, and this is shown through phase changes with the solid subliming into a gas. And so as the particles disperse a lot more from being a solid where they're all together to a liquid where they move more to a gas where they're pretty much anywhere inside the container, entropy increases. And entropy decreases when the gas goes to a liquid because it's coming together. And then that goes to a solid. So the entropy of a gas also increases when there's an increase in volume, as with an increase in volume, you have more space for the particles to spread out. And if moles of gaseous products are greater than gaseous reactants, then entropy generally increases, as you have more products in a reaction that's being created than you had reactants. So the matter gets much more dispersed. So measuring entropy. So entropy is measured in joules per Kelvin instead of kilojoules per mole. And the equation you can use to find the entropy or delta S is by summing up the values of delta S of S products minus S reactants. And if you don't have these values as shown over here in the problem below, you could just estimate it by determining if the entropy is positive when solid goes to a liquid goes to a gas, and negative when entropy goes from gas to liquid to solid. You can also estimate it by seeing how much moles there are in the product to the reactant side, and you can determine what the entropy is. So let's try this problem over here. So this one's asking us to calculate the delta S for the reaction. So you have to use this equation, delta S equals S products minus S reactants, and you have to use stoichiometry along with that. So our products are 1.75, well, PBI2 and 2KNO3. So let's start it. So delta S equals, so what we have is 1 mole of PBI2, so that's 175. Oh yeah, you have to put brackets, don't forget about that. Plus, as it's a summation, so you're adding it up, plus 2 times the KNO3, so the amount of KNO3 is 150. And you then subtract that from S reactants, which then you put another set of brackets, which is PbNO3 2, which is 250, plus 2Ki, so 2 times 125. You then, what you do is just add these up. So you have 475. Subtract that from 500, 250 plus 250. And so the answer would be negative 25. And so the only one that has that is A, negative 25. Along with that, we can estimate delta S as we have two aqueous solutions going to a solid and another aqueous solution. So entropy will slightly decrease as the dispersal of matter is decreasing. So we can just estimate that will be slightly negative. And so negative delta S is unfavorable, as entropy favors the reaction moving, dispersing a lot more than it does not dispersing. So let's go on to 9.3. So 9.3 is Gibbs free energy. So Gibbs free energy basically describes whether a reaction is thermodynamically favorable or not. And if the reaction is thermodynamically favorable, the reaction is spontaneous. And that's measured by delta G. So the main equation that you can use for this is delta G is the summation of delta G products minus the summation of delta G reactants. Along with that, you have delta G equals delta H minus T delta S. And you have the chart showing the delta H and delta S values and how that relates to delta G being favorable or unfavorable. So what you have, the most favorable is when delta H is negative and delta S is positive, as both delta H and delta S are positive or favorable. So if both of these are favorable, then at all temperatures, delta G will be favorable. For delta G, when delta H is positive and delta S is negative, both of these are unfavorable, right? So as both of these are unfavorable, the delta G will be unfavorable at no temperatures. Oh, my bad. Delta for when delta H is negative and delta S is negative, that basically is showing that delta S is basically unfavorable. So when you have this equation, delta G equals delta H minus T delta S, if you have low temperatures, as delta S is unfavorable, it'll be able to, well, be favorable. Delta G will be thermodynamically favorable at low temperatures, because if you have higher temperatures for delta S, then it'll become positive delta G. So delta G is only spontaneous at low temperatures. And you also have delta H is positive and delta S is positive. And if that's true, delta H is positive at spontaneous at high temperatures. So yeah. So we have a problem over here, which is basically giving this reaction and then showing. So it is observed that the reaction producing KCl from its elements goes essentially to completion, meaning that it's spontaneous. So delta G is favorable. So which of the following is a true statement about the thermodynamic favorability of the reaction? So the reaction is favorable as it's occurring, and because delta H is negative, delta H is favorable, while delta S is not favorable, because first of all, it's the amount of products is less than the amount of reactants, and also you don't have any dispersal of matter. So delta S would be negative. So the main thing that's driving the reaction is an enthalpy change. So it would be A. If you didn't know what to do, you would just see that it goes essentially to completion, and you can infer that delta G is favorable, so you can take out B and D. And also you can see that the amount of products is less than the amount of reactants, meaning delta S or entropy is unfavorable, so C is gone. So A is the best answer that we have. 9.4. So the thing is, some reactions are thermodynamically favorable but do not occur at a measurable rate, and this is known as kinetic control. So in kinetic control, catalysts can decrease activation energy and increase reaction rate, even if the reactions are thermodynamically favorable. So we have this problem over here. So consider the reaction represented above at 298 Kelvin. When equal volumes of N2 and H2, each at 1 atm, are mixed together in a closed container at 298 Kelvin, no formation of NH3 gas is observed. Which of the following best explains the observation? So let's try this. So first option, so the N2 and H2 must be mixed in a 1:3 ratio for the reaction to occur. This is wrong, as basically Well, you don't need to have it be in a ratio. You can have it in any amounts, but then there are limiting and excess reactants. So this is wrong, and it won't affect the formation of NH3. The reaction has small equilibrium constants, so thus no product will form. That will also not be true since you don't have the information over here for that. And as delta G is negative, it is thermodynamically favorable. So there's like a whole set of equations on delta G and how that relates to the equilibrium constant. So that'll be in the next couple units. The reverse reaction has a lower activation energy than the forward reaction, so the forward reaction does not occur. That's not true either. And so B, a high activation energy makes the forward reaction extremely slow at 298 Kelvin. So that's the best one, as basically delta G is negative, so it's thermodynamically favorable. So it's basically under kinetic control. And so in order to remove that, you have to add a catalyst. So B is the best choice that we have. 9.5, free energy and equilibrium. So thermodynamic favorability means that products are favored at equilibrium. And that's shown with the equation delta G equals negative R times T times the natural log of K, or the equilibrium constant. So when delta G is negative, K is greater than 1, so the products are favored. When delta G is positive, K is less than 1, so the reactants are favored. And when delta G is equal to 0, the reaction is at equilibrium. And this ties to the problem we just completed. So, yeah. 9.6, coupled reactions. So making unfavorable processes happen. So delta G, a positive delta G is unfavorable. And there's two ways in order to make a reaction that's unfavorable occur. You could either hook it up to an external source of energy, or you could couple reactions together. And so to do that, you have to have two reactions that share a common intermediate. And so you have to use Hess's law in order to do this. And the sum of reactions will be negative. So let's try this problem out. So we have Fe2O3 makes 2Fe plus 3 over 2 oxygen, and delta G is plus 742 kilojoules. And you also have CO plus 1/2 O2 creates CO2. And so you're trying to get to equation 3. So equation 1 is all good, but equation 2, in order to cancel out the oxygen, as that's our common intermediate, you have to multiply both sides by 3. So times 3, then times 3, and then you have to multiply delta G times 3. So that'll be CO, 3CO plus 3 over 2 O2 creates 3CO2. And delta G, and you can use a calculator to solve this, is negative 850.5 kilojoules per mole. And so now you can cancel out the oxygen, which is common intermediate, so you get the same equation that you had before for equation 3. So you then have to add up the delta G values. So plus 742.2 minus 850.5. And so you can use a calculator. So 742.2 minus 850.5 is negative 108.3 kilojoules per mole. And that is thermodynamically favorable. So thermal drawings, okay. 9.7, Voltaic and electrolytic cells. So an electrochemical cell is basically a cell, it basically converts energy that's released by a redox reaction into electrical energy, or can drive a thermodynamically unfavorable reaction. So a voltaic cell involves a thermodynamically favorable reaction, and an electrolytic cell, which is another type, involves a thermodynamically unfavorable reaction. Both contain an anode, which is the oxidation half of the reaction, and a cathode, which is the reduction half of the reaction. So let's go to the next one. So voltaic cell components. So the anode is where the oxidation occurs. And so the anode can be a reactant that's oxidized or an inert solid. If the anode is a metal, the mass decreases as the metal loses electrons when converted to ions. And like, I'll try to explain this whole thing out. So basically what you have is when something's being oxidized, it loses, oxidized is losing electrons. Yeah. So over here, it's being oxidized. So the copper metal is losing electrons and turning into Cu2 plus. And so what that Cu2 plus does is that it goes to the salt bridge, and it meets up with the NO3 minus. And the electrons from here, they go to the voltmeter where they get measured, and then they go to the Ag plus and to the Ag. And so as there's Ag plus cations, the electrons add up. So the mass of the Ag gets higher while the mass of this copper gets lower. And then, yeah. So basically, the mass of the cathode increases as the reaction progresses, while the mass of the copper decreases while the reaction progresses. So electrolytic cell components. So electrolytic cells are thermodynamically unfavorable, and so they require a battery as a power source. So these are single chambers, so you don't need a salt bridge, and the electrons flow from the anode to the power source to the cathode. And this occurs in an ionic solution or a liquid. So let's try this problem. So 9.7. So which half contains the anode, the right or the left? Justify your response. So basically what's happening over here is the aluminum is losing its electrons. So the electrons are going from here to the voltmeter and then going down. So the left side has the anode, as the aluminum ions are basically losing their electrons. And let's do part B. So what happens to the mass of the zinc electrode as the cell operates? So as the electrons are being removed from the aluminum, the mass of the aluminum decreases. So as the mass decreases, those electrons go to the zinc. And as the zinc gains those electrons, the mass of the zinc half cell will increase. So, yeah. 9.8, cell potential and free energy. So standard reduction potential. So these basically determine voltage or the electric potential difference. And the symbol for this is E, which is energy, and the unit for it is V, which is volts. And these are only accurate under standard conditions, which is 25 degrees Celsius, 1 atm, And the table only gives reduction potential. So if you want the oxidation potential, you have to reverse this reaction. So what you have to do, let's say for F2 plus 2E minus, it makes 2F minus, 2 fluoride. And so it just becomes 2 fluoride makes F2 plus 2 electrons. And the standard potential, if you flip it, is negative 2.87. So standard cell potential. So E cell, which is basically E cathode, which is the reduction, minus E anode, which is oxidation. And this does not depend at all on the amount of substance that's reacting. Thermodynamic favorability. So voltaic cells are thermodynamically favorable because they have a positive cell potential. And electrolytic cells are thermodynamically unfavorable due to having a negative cell potential. So let's try this problem over here. So what we have over here is the anode is the aluminum and the cathode is the zinc. So anode is basically being, as it's losing electrons, it's being oxidized. So oxidized is anode and cathode would be reduced or it's gaining. So basically what you have to do over here is you have to flip it. So you have Zn 2 plus 2 E minus makes Zn. And you also have to flip it as Al. You have to make it Al plus, oh wait, my bad. Al creates Al3 plus 3 E minus. And so what you have to do is you have to find the amount that's of electrons that would match up. So there's 2 electrons for Zn, 3 electrons for Al. So you have to find a common number, which would be 6. You have to multiply both sides. So you have to multiply the zinc by 3 times, and then you have to multiply the aluminum by 2, so 2 times. So 2Al makes 2Al3 plus and 6 E minus. And you have 3 Zn2 plus 6 E minus makes 3 Zn2 plus. So you can cancel out the electrons. So you have 3 Zn2 plus 2 Al, 2 aluminum creates 2 Al3 plus plus 3 zinc. Now it's asking us to determine the standard cell potential of E dot cell for, and so what we have to do is E cell is E cathode minus E anode. So E cathode would be Zn, so that would be negative 0.76 minus, so aluminum, you have to flip it as it's being reduced. Actually, you don't have to do that. My bad. Sorry. Minus negative 1.66. And that would just be 0.90 volts. So clear the drawings. And you have another thing that we're going to add, which is Faraday's constant, which is 96,485 coulombs per mole electron. And an equation to use delta G is you can use delta G equals N, which is negative N, which is the number of moles of electrons, times Faraday's constant times E dot cell. And a positive E dot cell is a negative delta G, meaning it's favorable, and a negative E dot cell is a positive delta G, which is unfavorable. So let's try this problem over here. So write the balance equation for the reaction occurring in the cell. So this is same as we did before. So what we have to do is we have to flip it. So Fe2 plus. So I guess we can just try it like we did before. So you have 3 Fe2 plus. As you have to multiply these by 3, and then you have to flip it, and then you have to multiply by 2. So plus 2Al. And so as there's 6 electrons, you can cancel these out. They don't apply anymore. Makes 2Al3 plus plus 3Fe. And now you have to calculate E cell, and I'll just erase the drawings. And so for E cell, what you have to do is you have to do, I'll do it here. So E equals E cathode, which the cathode is Fe, so negative 0.45. Minus E anode, which is negative 1.66. And E will equal 1.21 volts. So part C. Does the concentration of Al3 plus in the solution increase, decrease, or remain the same as the cell operates? Explain your answer. So the concentration of Al3 plus increases as the cell operates, as Al3 plus is a product of the reaction, not Al. So as Al3 plus is in the product, it's being increasing while the reaction continues as the electrons go from the Al regular to the Fe, and so there'll be more Al3 plus as those electrons go and continue. So calculate the standard free energy of the reaction. So the amount of moles of electrons in this reaction would be 6 moles. So let's do this over here. So 6 moles E minus, which is N, and then E cell is 1.21. And you can use your calculator because I'm not sure they want you to multiply 96,000 by 1.21 times 6. So delta G, delta G, good. So delta G equals negative 6 times 96,485. Multiply that by 1.21. And so that will be negative 7 times 10 to the negative 5, without sig figs, joules. And that's our answer for the free energy of this reaction. So the last one is the value of the equilibrium constant KQ at 25 degrees Celsius greater than, less than, or equal to 1. So the equilibrium constant would be greater than 1 as the amount of, oh, I forgot to put a negative. I'm not sure. So it'll be greater than as delta G is negative. So as delta G is negative, it indicates that the reaction is favored to the products, so that the K is larger than 1. So yeah, that's 9.8. So 9.9, cell potential under non-standard conditions. So cell potential depends on concentrations of pressures and reactants. Standard conditions are defined as 1.0 molarity and 1.0 atm gases, which correspond to Q, or the reaction quotient, equaling 1. Standard cell potentials will apply under these conditions. And as the cell operates, reactants are consumed and products are produced, meaning their concentrations change. Changing mass does not affect cell potential. Equilibrium in E cell. So when Q equals 1, E cell is not at equilibrium, and as the system approaches equilibrium, cell potential decreases. In a voltaic cell, K is greater than 1. So when Q is above 1, the system is closer to equilibrium. When Q is below 1, system is farther from equilibrium. So the question is asking which of the following occurs if the silver electrode is made larger. So the silver or Ag, so if the electrode itself is made larger, the voltage does not change, as basically silver is a solid and it doesn't appear in any of the equilibrium or Q expressions. So the voltage will not change at all. It will not affect Q or voltage. So that's our answer. So now we have the last subunit of AP Chem, 9.10, electrolysis and Faraday's law. So charge flow and electrolysis. So the amount of charge is a function of the current and the time. So basically that's shown by I equals Q divided by T. And Q is related to changes in amounts of reactants and products in the cell. So solving problems like this. So you have to have an attention to units in dimensional analysis. So current is in amperes or A, which is also coulombs per second, C over S. So time needs to be in seconds, and Faraday's constant is 96,485 coulombs per mole of electrons, and the moles of electrons is determined by the chemical equation. So let's try this over here. So what you have is 0.125 grams gold. And so AU, what we have is the equation for this is AU 3 plus 3 electrons will make AU or gold. So the amount of the ratio of AU, 1 mole AU is 3 moles of electrons. So 1 mole so 3 mole. And also you have to get the molar mass of AU. So molar mass is, when I look it up, it's 196.97 grams per mole, or 197 grams per mole. And so you have to set up a dimensional analysis. So basically what you have over here is you have 0.125 AU, and put units, it just makes life easier. So then you have to use the molar mass, which is 197. One mole AU. And for this reaction, you have 1 mole, 3 moles of electrons. And so what you have is 1 mole E minus is also 96,485 coulombs. So and with those coulombs, then you finally have to convert to the amperes. So amperes is coulombs per second. So what you have is you can have it be 0.800 coulombs for every 1 second. And so determine the time required. So that basically gives us a value of approximately 230 seconds. So yeah, that's our answer. So it takes 230 seconds for the gold to be electrolyzed. So that's how you do problems like this. It's honestly quite simple if you know the constants and all of that, and it's just you have to practice it again and again, you'll get it. So yeah. Well, I guess that's it. So I'll be also finishing up the Unit 2 and Unit 4 videos by the 24th. And other than that, I hope you all do very good on your AP tests, and I hope you all stay safe.